this is 12% of a grade, and this is what the final exam is going to be on. Okay. So what is a graph? Now we have already seen some type of graph already. So all the trees we have seen can be called as a graph. So later I'll tell you when you can call a graph as a tree and when you cannot call a graph as a tree. So a tree is also a type of graph. Okay. So basically we have seen these terminologies, as I said, because a tree is also a graph. So a vertex and an edge. So a graph is a data structure. It's a collection of nodes, also called vertices, and links, also called edges. So you're going to have basically the circles called nodes or a vertex, and lines connecting two vertices, they're called links or edge. Now the edges in the graph could be directed or undirected. So accordingly we can call a graph as an undirected graph or a directed graph. Now, what could be an application of a graph? There are a lot of applications of graphs. So there's a whole area called network science that deals with graphs. Okay. So any complex real-world network could be modeled as a graph. So, for example, a network of cities. So each node could be a city, and an edge could represent the road that connects the two cities. So if you want to find out how to travel from one city to another city, then you can run an algorithm on the graph and find out a path between two nodes and so on. It could be a network of airports that if you want to travel, you can find through what intermediate airports you have to travel to go from one airport to another airport. Or even social networks, so all your Facebook and all the social networks, the people you know can be like two people know each other, so that's a link between the two people, so that's a social network. Communication networks, again, so each node could be a network, and there's a link between two networks if the two networks are connected to each other through a communication channel. Now again, if the edges are directed, that means you can have communication. So typically a graph, the edge represents some form of communication. So in an undirected graph, it's like the communication can be in both directions. So you can send something from 0 to 1 as well as from 1 to 0. So that's what a communication, that's what an undirected edge means. In a directed case, you can kind of send information or talk or whatever the way you model the graph from only in one direction. So in this case from 0 to 1 and 1 to 3 and so on. So a good example could be the Twitter, who follows who. So if you model the edge like if a node follows another node, there's an edge from the one that is following. So 0 follows node 1, node 1 follows node 3, node 5 follows node 3 and so on. So that Twitter is a very good example for a directed graph. Now, how do you store the graph information? Now, there are two ways we can store the graph information, either as an adjacency list or an adjacency matrix. So an adjacency list is basically for each node you store what is called the neighbors. So now you should know what's the neighbor for a node. So neighbor is nothing but the edges that are attached to a node. So for 0, 1 and 2 are the neighbors. So the edges attached to node 0 are incident on node 1 and node 2. So those are called the neighbors of a node. So for node 1, 0, 2 and 3 are the neighbors. For node 2, 0, 1 and 4 are the neighbors. For node 3, 1, 4 and 5 are the neighbors, and so on. So you store only the neighbors of a node. Now if you think about how to implement it, so even though we are not looking at implementation of graphs, so as we proceed I'm going to talk about a lot of implementation details. So if you really want to program on graph, you can make use of this, and in the summer for example you can implement a graph using all these implementation details. So what are the neighbors of node 4? That's the question. So neighbors of node 4 are 2, 3, 5 and 6. So basically whichever nodes you have at edge, those nodes are called the neighbors. Okay. Um, so you just store the neighbors for each node. So 0, you have 1 and 2. For 1, you have 0, 2 and 3 as the neighbors. For 2, you have 0, 1 and 4. For node 4, as I just mentioned, 2, 3, 5 and 6 are the neighbors. So now if you think about how to implement it, we have already seen something similar to this. So you can maintain an array of linked list. Okay, so if your node IDs start from index 0, so the node IDs are the index to this array, and each list of neighbors is a linked list. So 1 and 2 will be at the linked list for node 0, 0 to 3 or the data in the linked list for node 1 and so on. So this is nothing but an array of linked list if you really want to implement it. Now you can also store information about a graph in the form of what is called an adjacency matrix. So an adjacency matrix is a square matrix and the entries are binary, 0 or 1. So how many entries depends on the number of nodes. So here you have nodes from 0 to 6. So those are the row IDs. So this is called the row IDs and this is called the column ID. So basically these are the node IDs. And there is a 1 for an entry if there's an edge between the two nodes. So there's a 1 here because there's an edge between 0 and 2. There's a 1 here because there's an edge between 0 and 1. Now there's a 0 here because there's no edge between 0 and 3. There's no edge between 0 and 4 and no edge between 0 and 5 and so on. So that is how you fill the adjacency matrix. So an entry is a 1 if there's an edge between two vertices, and an entry is 0 if there's no edge between two vertices. Now an undirected graph, for an undirected graph, the adjacency matrix is going to be kind of like a symmetric matrix. So what I mean by a symmetric matrix, so if you know from math, a symmetric matrix is the upper triangle is going to be a mirror reflection of the lower triangle. So you see here, so for node 0, the neighbors are 1 and 2. So you have 1 and 2, you have entries of 1 and the other is 0. So this row entry is same as this column entry. Because this is an undirected graph, this column also captures that information. That node 0 has an edge to node 1, has an edge to node 2, but no edges to nodes 3, 4, 5, 6. So that's why this row for node 0 is same as the column for node 0. The row for node 1 is going to be the same as the column for node 1. So node 1 has an edge to 0, has an edge to 2, has an edge to 3, but to nothing else. So that's the case. So the row for a node is same as the column for that node. So that makes the matrix symmetric. So it means, so if it is 1, 1, 0, 0, 0 here, that's 1, 1, 0, 0 here. And also one thing I should notice, I should tell is the diagonal entries are always going to be 0. So the dotted line here is the diagonal entry. So why they're all 0? Because they represent the node to itself. So this is from node 0 to node 0, node 1 to node 1, node 2 to node 2, node 3 to node 3. So unless there's something called a self loop, so that a self loop is like if you have an edge from say one node to itself, so node 3 to node 3, if there's an edge. So that's called a self loop, and that's the only case where you'll have 1 for the diagonal entries. So most of the real world graphs, of course there are a lot of real world graphs, especially in biological networks, that will have self loop. But in majority of the cases, we don't really come across a graph with self loop. So in this course, we'll not consider graphs with self loop. So the diagonal entry is always going to be 0 for the adjacency matrix. So that means 1, 1, 0, 0, 0 here is same as this here. Then consider everything to the right of the diagonal. So 1, 1, now these 3 zeros, same as this column, 1, 1, 0, 0. Then 0, 1, 0, 0, same as 0, 1, 0, 0. Now 1, 1, 0, same as 1, 1, 0. 1, 1, same as 1, 1. Then 1, 1. So it means if you can write the row to the right of a diagonal, you can write the column below the diagonal. That's what I want to say. So the row to the right of the diagonal is same as the column below the diagonal. So that's why I say it's a mirror reflection. using the diagonal as the mirror. Okay, so that is what a symmetric matrix means. An adjacency matrix from undirected graph is a symmetric matrix. So now there's one terminology called a degree of a vertex. So degree of a vertex is the number of neighbors of the vertex. So for node 0, it has 2 neighbors. So the degree of node 0 is 2. Node 1 has 3 neighbors. So the degree of node 1 is 3. Node 4 has 4 neighbors. So the degree of node 4 is 4. Node 6 has 2 neighbors, so the degree of node 6 is 2. So degree is just the number of neighbors for a node. So you can again just come up with a simple algorithm to compute the degree of the vertices. That's going to be just the size of this linked list for each node if you use an adjacency list. If you use an adjacency matrix, it's going to be just counting the number of ones. So the sum of the entries in the adjacency matrix for each node, if you just consider row or column, either way, because it's symmetric, you will get the degree for a node. Okay, so any question? Okay, so there's a question, which would you say is easier? So I think you're assuming either adjacency list or adjacency matrix, right? Okay. Now, yes, so the adjacency list seems to be a simple version, and it's also memory, it can save you memory, because if you look at it, an adjacency matrix, you have to store entries for all the possible combinations. So there are a lot of zeros in this matrix. So why? Because there are not that many edges, but you still have to store that information. So in adjacency matrix, you have to store information for all possible combinations of vertices. Whereas in adjacency list, you store only the edges that really exist in this graph. So for node 0, it has edges with 1 and 2 only, and you just store that information. You don't really need to store that it doesn't have edge with 3, 4, 5, 6. As in adjacency matrix, you need to store that information as explicitly as, like, there are no edges between 0 and 3, no edge between 0 and 4, and so on. So that way adjacency list is simple to look at, and also for all processing purposes. Now, if you look at the total amount of bits it's going to take, it may turn out that adjacency matrix is not that bad in terms of how much memory it's going to take, because if you implement this as a binary matrix, not as an integer matrix, if you allocate only 1 bit to store each of this information, then this is just 1 bit, another bit, and so on. So for each node, you spend less than a byte of memory. Whereas if you store the information as an adjacency list, you need to store the node IDs, and node IDs are integers, and each integer is, say, 4 bytes. So this information, this entry alone will take you 4 bytes for node, storing that node 1 is a neighbor of node 0, another 4 bytes to store that node 2 is a neighbor of node 0. So that means this entry alone, that 0 has 1 and 2 as neighbors, will take you 8 bytes to store in memory. Whereas this in adjacency matrix, you just spend less than a byte to store this row for node 0. So that way adjacency matrix is not very bad from a memory usage point of view. But to process an adjacency matrix, it's typically not that easy, because if you really want to count the number of neighbors for a node, you can just count the actual number of neighbors, whereas for adjacency matrix, you have to sum through all the entries. So it could be more time intensive for an adjacency matrix, and less time consuming with an adjacency list. So that's why, so if memory is not a real problem to use, then it's better to use adjacency list for all if you really want to save time. So an adjacency list based approach implementations will take less time and probably more memory because of the integer storage overhead I mentioned. Then adjacency matrix based implementations could take less memory, but still, since you're storing information for all pairs of vertices, you have really process all of them in order to decide something. Like for example, the degree, you have to really count all the numbers here before you decide the degree for a node, which means you have to really do like what, 6 additions or 7 additions if you start even from this 0 on the diagonal. Whereas here you just count the 2 integers out there and say there are 2 neighbors. So adjacency matrix based implementations are more time consuming, but they may be less memory intensive. Okay, so I hope this answers the question. That's a good question. Any other question? All right, so now let's look at the same thing for a directed graph. So you can use an adjacency list or adjacency matrix to store information for a directed graph. So again, in a directed graph, you have edge in only one direction. So adjacency list, again, you follow a convention and stay consistent with it. So with an adjacency list, you can follow the convention that if there's an edge from 0 to 1, okay, then you store that information. So there's an edge from 0 to 1, so you store 1 as what is called an outgoing neighbor. So from 0 you have an edge to 1, so 1 is considered to be an outgoing neighbor of node 0. Now from node 1's point of view, 0 is an incoming neighbor. Okay, so like for example, for node 2's point of view, its outgoing neighbors are just node 0 because it has an edge going out to only node 0. Whereas for node 2, the incoming neighbors are 1 and 4 because you have edges coming to node 2. So those are called the incoming edges. Similarly, for node 6, there are no outgoing neighbors because there's no edge going out of 6. So there are no outgoing neighbors of node 6. But there are 2 incoming neighbors, 4 and 5. So you follow a convention, you just store the outgoing neighbors or the incoming neighbors, and that will cover all the edges. So here we will store the outgoing neighbors. So for 0, the outgoing neighbor is node 1. For node 1, the outgoing neighbors are 2, 3 and 4. So you store that. For node 2, the outgoing neighbor is node 0. For node 3, there is no outgoing neighbor. For node 4, there is 2, 3 and 6. So those are the outgoing neighbors. Then for node 5, you have 3 and 6 as outgoing neighbors. Node 6, no outgoing neighbor. So if you look at it based on this information of outgoing neighbors, you have essentially captured all the edges, all the directed edges that are out there. So again, you can implement this as an array of linked list, and if there are no outgoing neighbors, that linked list is basically empty. Okay. Now again, for the adjacency matrix, you follow the convention. So between 2 vertices, there is an entry of 1 if now we have to look at the row and column index. So let us look at the math here. So Aij is 1 if there's an edge from I to j. So the row index is I, column index is j. So an entry is 1 if there's an edge from I to j. So this 1 means there's an edge from 0 to 1. This 1 means there's an edge from 1 to 2. This 1 means there's an edge from 1 to 3. This 1 means there's an edge from 1 to 4. The 0 means there's no edge from 1 to 5. Similarly, the 0 here means there's no edge from 1 to 0. Since edges are directed, there's an edge only here from 0 to 1, not from 1 to 0. So the entry for the cell 1, 0, row 1, column 0, the entry is 0 because there's no edge from 1 to 0. So you define how you want to store the information. So we'll follow the convention of storing just the outgoing neighbors, and that will again cover all the edges in the directed graph. Okay, any question? Okay, so just some terminologies of different types of graphs before you look at some graph algorithms. Now, a graph is a complete graph. Now, all these things are applicable for undirected graphs. Of course, there are some cases where you can also apply these terminologies for directed graphs, but let's just focus on undirected graphs. Now, if you have edges between any two vertices in the graph, okay, so there are 6 vertices in this graph and there's an edge between any two vertices in this graph. So such a graph is called a complete graph. So a complete graph means edge between any two vertices in the graph. Now a graph is called a regular graph if all the vertices in the graph have the same degree. And we generally call it as a k-regular graph if every vertex has degree k. Okay. So in this case, each vertex has degree 2. So that's why it's called a 2-regular graph. And there's also an interesting property. In a k-regular graph, there are a total of k edges. Okay, so in this case, there are a total of, I think I have to take it back. This I have to verify. No, this is not right. So I'll check. This is a function of k. It's not really a total of k. Okay, so I'll go back and check it. But right now, all you have to remember is for a k-regular graph, each vertex has a degree k. Okay. Now, a star graph. A star graph is like you have one vertex in the center and you have an edge to every other vertex. So it looks like a star. Okay. Now, so that means this vertex at the center has a degree what? It has an edge to every other vertex. So if there's a graph of n vertices, this vertex as center is going to have a degree n minus 1 because it's connected to every other vertex. So that's the degree of this. This vertex is called hub vertex because it is like a hub to which everyone else is connected. So the degree of a hub in a star graph is n minus 1, whereas every other vertex has degree 1. That's what is a star graph. Now, where is this tree come? Okay, so a tree is also a graph. The thing is, a tree should not have any cycle. So that means, what is a cycle in a graph? A cycle in a graph is a subset of the edges such that you can start with one vertex, go around those set of edges and come back to starting vertex. So in this case, these edges starting from here, you can go to this vertex, then go to this vertex, then go to this, and then come back to this vertex. So these 4 edges are said to form a cycle. Similarly, these 4 edges also form a cycle, and also these 6 edges are the boundary, not the one in the center, the middle. Other than the edges in the middle, all these other edges in the periphery, these edges also form a cycle. Okay, so the edges like here, so in the periphery they form a cycle. So that's what you mean by cycle, and a tree should not have any cycle. Okay, so in all the trees we have seen so far, the binary trees, everything, we don't have any cycle. Okay. And one interesting property of a tree is you have only one path between any two nodes. So if you take from this vertex, you want to go to reach this vertex, you have to take this path from this node to this node and reach this node. So you have only one path between any two vertices in a tree. Whereas if a graph has a cycle, you have more than one path between the vertices that are part of a cycle. Just look at this example here. So between these two vertices, the top and the bottom one, this edge itself is a path, because a path is nothing but a sequence of edges between two vertices. So this is a path between the two vertices, as well as you can go through this two intermediate vertices and then reach this vertex. So you have two paths here, one path like this and another path like this. As well as you can go, it's not just two, you can also use this cycle. So there are 3 paths between these two vertices. So you have more than one path basically. between two vertices that are part of a cycle. So if you have more than one path between any two vertices, that graph is not a tree. Okay, so this is something you should know the difference. So when can we call a graph as a tree? We can call a graph as a tree if there's no cycle in the graph. That means there's only one path between any two vertices in the graph. Okay, so that will save this as a video. You can type or ask any question.